2 of theta as the 1 in the 2, 2 place of the matrix. With the negative in the lower left rather than the upper right corner. And then R3 is the rotation around the z-axis. It has the 1 in the 3, 3 entry of the matrix. Right? So these are our fundamental rotations. And then we have, I guess he set us up. Okay. And then we have the ZXZ Euler angles. We have any number of different kinds of Euler angle schemes, but the 3, 1, 3 or ZXZ Euler angles would be of the form alpha, beta, gamma, R3 of alpha, R1 of beta, R3 of gamma. And so that's rotations. And then as far as angular velocity is concerned, we have that the space-fixed version of angular velocity was the vector of r dot times r transpose, and the body-fixed version of angular velocity was r transpose r dot. The vector of this, remember, these are skew-symmetric matrices. We went through and proved that. And these are related to each other by the general fact that if Q is a rotation matrix, then, so here Q is a rotation matrix. Then, and if omega is a skew-symmetric matrix, then Q omega Q transpose is also a skew-symmetric matrix. And if we take the vector of this skew-symmetric matrix, then this is Q omega, where omega is the vector of the skew-symmetric matrix, capital Omega. Remember that this vector operation is what we get by taking a skew-symmetric matrix that's labeled in this way. It has the entries labeled like this. And the vector of that is what we get by taking the omega 1, omega 2, and omega 3 and putting them into a vector like this. Okay? So that's the essentials of rotations and angular velocity. So this is the same as saying that omega s, so this together with this fact, so this fact is true for any Q being a rotation matrix and any skew-symmetric matrix. If we apply this rule to the particular case where this is our skew-symmetric matrix and the Q is R, as a special case, we get that the space-fixed version of the angular velocity vector is equal to R times the body-fixed version. And so this statement looks a lot like the position vector as seen in the space-fixed reference frame is equal to the rotation that's performing the rotation from space-fixed to body-fixed times the body-fixed description of the vector. So the same rotation matrix implements the rotation from the space-fixed frame to the body-fixed frame. And that's the same rotation matrix that you multiply a description in the body-fixed frame to get the space-fixed description of the same vector. Okay? So, so there's only one rotation matrix you really need to remember. It does the same thing. It implements the rotation going from space fixed to body fixed, and it takes the description of a vector in the body fixed frame and converts it to the space fixed description of the same vector, the same position vector pointing to the same physical point, but viewed in the two different reference frames. Okay? So that's part of our review. And the other part is we went through and derived Lagrange's equations. And again, that's for conservative systems, systems where the sum of the kinetic and potential energies add to a constant. There's no gain of energy or no loss of energy in a conservative system. And we're going to put these things together today in looking at the dynamics of a spinning top. So these Q's can be any generalized coordinates, including the case when we're looking at the three Euler angles as our generalized coordinates. So that's what we're going to be doing today. We're going to be combining these things. Just as a little side note before we start, there's certain notation that is used. So when talking about the set of all possible 3x3 rotation matrices, this is the set of all such matrices is called SO3. So I'm just going to talk a little bit about this terminology. We're not going to need it very much in this class, but just like learning about the bug in the code and DYs, linearize, it's sort of cultural background that we're going to talk about with regard to this name. So what does SO3 stand for? So SO means special orthogonal. And so R transpose R is equal to the identity matrix. That means that's equivalent to saying R is orthogonal. An orthogonal matrix is one which has, so this statement is the same as saying that R transpose is equal to R inverse. An orthogonal matrix is one whose columns, in this case it's a three-dimensional matrix, so it has three columns. An orthogonal matrix is one whose columns are all orthogonal to each other, perpendicular to each other. So the dot product of A with B is equal to 0, the dot product of B with C is equal to 0, the dot product of A with C is equal to 0. So that's what orthogonal means, and that's the same as this condition up here. Okay, and equivalent to that is that the inverse of the matrix is its transpose. So that's what orthogonal means, and special means that the determinant of R is equal to positive 1. So a matrix is called special if its determinant is equal to positive 1. Now these two conditions are independent of each other. You can have matrices that are special without being orthogonal, and you can have matrices that are orthogonal without being special. But only when both are satisfied do we have a rotation matrix. So for example, so here's an example of special but not orthogonal. Okay, 1, x, y, 0, 1, z, 0, 0, 1. Okay? A matrix like this, the determinant, because it's upper triangular, for an upper triangular matrix, the determinant is simply the product of the entries on the diagonal. So the determinant here is just 1 times 1 times 1. So this matrix is special. It has a unit determinant, but it is not orthogonal. If I take the dot product of this column with this column, I get x, right? X doesn't have to be 1, so it doesn't have to be 0, rather. If I take the dot product of this with this, I get x times y plus z. It's not going to be equal to 0 in general either. So this is an example of a matrix that is special but not orthogonal. An example of a matrix which is orthogonal but not special would be -1, 1, 1. The dot product of each column here with each other column is equal to 0, but the determinant is equal to -1, not +1. Okay? So rotation matrices are often called special orthogonal matrices, and actually they have a nice property that if you take any two rotations and you multiply them together, you get a rotation back. So, for example, so this, again, this is just notation. If I say that I give you two rotations, how do you actually prove that the result is a rotation? So suppose that R1 is a rotation matrix and R2 is a rotation matrix. So in other words, they are both elements of SO3. They are both rotation. This just means R1 and R2 are just both 3x3 rotation matrices. Okay, so what if we multiply those two rotation matrices? Is that going to be a rotation matrix again? Well, let's prove it one way or another. So if I take R1 times R2, and I call that R, and I put that into this equation here, we can check whether it's going to hold or not. So R transpose R is going to be equal to R1, R2 transpose times R1, R2. But we have this transpose rule that we talked about before. So we can use the transpose rule here. So this is R2 transpose, R1 transpose, R1, R2. So the R1, R2 is here. This term is just the transpose rule. People are smiling. I think you've seen it before. Maybe more than one time or something. I don't know. So R1 transpose times R1 is equal to the identity matrix. And the identity matrix we can just forget about. So this is equal to R2 transpose times R2. And then this, again, because R1 and R2 are both assumed to be, that's the premise of our statement here, is that R1 and R2 are both rotation matrices. We're asking if we multiply them, do we get a rotation matrix back? Then, and the answer is at least we get an orthogonal matrix back because of this little rule here. The result of the product of two orthogonal matrices is itself orthogonal again. Right? That's what we've just shown. Now, let's see if the determinant condition holds. Well, determinant of R1, R2, there's a determinant, right? We have a product rule, a transpose rule and a determinant rule for matrices. The determinant rule says the determinant of the product of matrices is the product of the determinants. And since R1 is a rotation, its determinant is equal to +1. And since R2 is a rotation, its determinant is +1. And if I multiply 1 times 1, I get 1. So in fact, both the orthogonality and the special property of the determinant being positive 1 hold for the product of two rotations. So this sort of describes what we knew was true already, which is that the determinant of the product is the product of determinants. The transpose of the product times the product is equal to the identity. In other words, if R1 and R2 are both rotation matrices, then when I multiply R1 times R2, the result will also be a rotation matrix. So R1 and R2 in here means that R1 times R2 is also a special orthogonal matrix. That's what we've just shown. Okay? Any questions about that? Who's seen that before? Okay, so maybe a third of the team. So I aim to present something new for 2/3 of the people, 2/3 of the time. How about that? So here's another little thing that we can do, and this is all a side note. Now, okay, here's a top, a gyroscope, and if I put it here and I let go, what's going to happen? It's going to fall down, right? Okay, that's no big surprise. And this is probably not a surprise either, but again, I'm only aiming to present something new to 2/3 of the people 2/3 of the time. So, you know, roughly speaking, most of you know most of what I'm going to be talking about the whole class, but we do what we can. So, I can thread this correctly. So I'm going to thread this, and then I'm going to pull on it. So I'm going to torque up this heavy rotor here, okay? And then I'm going to set it down, and then I'm going to let go. So what's going to happen when I let go? I'm going to torque this up so this is spinning very fast. Then I'm going to set this down right here, and I'm going to let it go. So what's going to happen? Okay, it's going to spin. It's spinning around its own axis. Is that the only way it's going to spin? What else is it going to do? It's going to gyrate around. Okay. So, well, that's a good guess since it is called a gyroscope. Okay, so let's let it go. Okay. So I let it go, and it goes around like that. Okay. Now it's going around at a specific speed, and the rotor is spinning at a specific speed. And if there were no friction, it would just keep going. And that's what we're going to model today, because that's all we know how to do, is model a conservative system that neither gains energy or loses energy. Okay? And you know, the bearing there is fairly frictionless, so this can spin for a while. But eventually, as energy gets taken out of the system due to air resistance and due to the contact there, and due to friction of the bearings of the actual rotor, it's losing energy. So that rotor is losing speed, and as the rotor loses speed, the angle droops down. And the rate at which this thing is nutating, okay, so actually we have three Euler angles, alpha, beta, gamma. Alpha dot, beta dot, and gamma dot each have their own names, okay? And actually alpha, beta, gamma have their own names also. You know, the alpha dot is called the nutation rate. Oops, see there you go. You can have the angle go way down and it still works. Okay. It's not touching the table. Well, it's touching the table now, but it wasn't touching the table originally. You can have, if I had this standing up higher, you can have this go down almost to 90 degrees and it will spin, it will mutate around like that. So the axis around the pivot there is actually our gamma. Okay, so gamma dot is how fast this heavy wheel is spinning. Okay? The beta is the angle that this makes relative to the vertical, the z-axis pointing up. That's what beta is. And the angle going around this way, that's our alpha. Okay? So what we're going to learn today is how alpha dot, how much this is nutating around like this, is related to the spin rate. Okay? That's what we're going to learn. And that depends on the angle beta. Okay? If this rotor is spinning at some particular rate, and I set this out at a particular angle from the vertical, then the amount that the rate of spin around the world frame z-axis is going to be different, and it's going to depend on the angle that I set this at. Okay? So that's what we're going to hopefully get through today, and it will involve both Lagrange's equations and what we know about angular velocity and Euler angles. Any questions so far? Okay, so let's solve the problem. So there was one little piece of review that we didn't go through yet. Now, by the way, in my notes, instead of alpha, beta, gamma, and in the homeworks, I use, so alpha, beta, gamma, right, are three angles. Oftentimes what's used, and what was used in my notes when I wrote these up, were phi, theta, and psi. Right? It's sort of like calling variables ABC, or actually ABG in Greek, or XY, Z. Well, not exactly, but you know, you get the picture. So, so I'm just going to use these variables, phi, theta, and psi, because that's what's consistent in the notes. But it's not hard to make a conversion, right? So these two. So theta will be the angle measured from the vertical. Phi will be the angle going around this way, and psi is the angle around the axis of the rotor. Okay, so what we discussed at one point was what is actually the space-fixed and the body-fixed angular velocity, and that was part of your homework to work out some of this. So if we actually work it out, you can either work it out from first principles, in which case this is r dot r transpose the vector, and this is r transpose r dot the vector. Or we can say that this is r times omega b. So if we do this one first, and then pre-multiply the result by r, we can get that. Or we could work this out by, as I did in class, I did it for this one, the r transpose times r dot, we get some cancellation, etc. And those answers, the space-fixed version of the angular velocity, if we use these variable names, then is equal to phi dot sine theta sine phi plus theta dot cosine phi negative phi dot sine theta cosine phi plus theta dot sine phi phi dot plus psi dot cosine theta, and the omega b is equal to phi dot sine theta sine phi plus theta dot cosine phi phi dot sine theta cosine phi minus theta dot sine phi sine psi psi dot plus phi dot cosine theta. Okay? So they look quite similar with some switching of phis and psis, and some switching of some sines, but they're not the same. Okay? They're, you take one, you multiply by r, and you get the other. And these can be written in a slightly different form. What we can do is we can extract out all of the dot quantities and write them as a vector. And again, this is a vector in the computer scientist sense of the word vector, and it's an array of numbers. It's not like a physical quantity that transforms as a one tensor as opposed to a two tensor. We talked about the angular, we talked to, actually, so this is how a vector transforms. You have something in the body frame, you hit it with a rotation matrix, you get its description in the space-fixed reference frame. That's how a physical vector transforms under a change of perspective. Here there's no change of perspective or anything, it's just a bunch of numbers written as a column. Okay? So, and we can, so if we extract these out, we can write a matrix here that has embedded in it the remaining dependence on phi, theta, and psi. Okay? So what is multiplying phi dot? Well, there's nothing multiplying phi dot here. What's multiplying theta dot? We have a cosine phi. What's multiplying psi dot? We have a sine phi sine theta. Okay, in the second row, what's multiplying phi dot? Again, nothing. Then what's multiplying theta dot? We have a sine phi. And what's multiplying psi dot? We have a negative sine theta cosine phi. And then the last row here, we do have something multiplying phi dot. And we have nothing multiplying theta dot. And then we have a cosine theta that's multiplying the psi dot. Okay? Now, these quantities have names, so it's convenient to say, call again, the vector in the sense of an array, phi, theta, and psi, ordered in that way. And it's convenient to write this matrix as, we'll call it J of phi. Okay, it depends on phi, theta, and psi. Actually, it only depends on, it doesn't depend on psi, but we'll still just write it like this way, and which means that it's constant. This phi vector is phi, theta, psi, but this matrix J is constant for different values of psi. So no matter what value of psi you put in, it doesn't affect this matrix. But we can still think of it as a matrix function of all three variables. In other words, I give you a vector phi, and this provides a matrix of numerical entries in it, which depend on the numerical entries of the vector phi. Okay? And because we're talking about the space fixed here, let's call this J space fixed. And so let's work this out. And this is going to be phi dot. I'll turn off my ringer here. And so we can write this whole thing as omega s is equal to J of phi times phi dot. Now, this is not J times phi dot. This is J of phi times phi dot. This is a matrix function. If we want to highlight that, we can put brackets around it and say, this is a matrix multiplying this vector. This matrix happens to depend on the value of phi, and we multiply it times phi dot. Okay, this is Js. And this, we can do the same thing over here. And if we extract out these, what's left in here is going to depend on the phi and theta and psi. In this case, it depends on theta and psi, but not on phi. Over here, it depended on phi and theta, but not on psi. And just because this is omega b, we're going to call this J sub b, the body fixed matrix. And this has a phi dot, so it's multiplying sine theta, sine phi. Then we have a 0 and a cosine phi. Here we have a sine theta, cosine phi, and a minus sine phi. We have a 0 here. And here we have, no, I'm sorry, I have it reversed. Both of these reversed, actually. Sorry. So this is theta dot, is the middle one. This is cosine phi, 0, negative sine. I said phi, but it's psi. Okay. So we have this, and then over here we have a cosine theta multiplying the phi dot. We have a 0 here, and then we have a 1 multiplying the psi dot. So does that look right to everybody, or did I make an error? It's okay? Okay. So this, the reason why I'm using the letter J for these matrices is because these matrices are called a Jacobian matrix. And they relate the rates of the three Euler angles to the actual angular velocity. So the angular velocity is this physical quantity, and the Euler angles are just a description of the physical quantity. And so actually, but in the case of the top, they're a very good choice of coordinates because they're describing exactly what goes on. But Euler angles can also be used, to do a simulation. If I throw this eraser, Euler angles can be used to simulate how this eraser is moving. There are no physical axes like there is in the gyroscope for this eraser, but we can still use the Euler angles to describe rotational motion in space of any body. The only problem with them occurs when, so you can think of the Jacobian matrix as a way to convert between these rates and the angular velocity. So if I give you these rates, you multiply this matrix, and you get the angular velocity. Suppose I give you the angular velocity, and I tell you what the Euler angles are at that time. How would you get these rates? So suppose I give you this, and I tell you what these entries in this matrix are. How would you find these? You'd invert the matrix, right? But to invert a matrix, it has to be invertible, right? Now, what is the condition for a matrix to be invertible? That's right. The determinant cannot equal to 0. So let's calculate the determinants of these matrices and see what they are. And that will tell us if we can invert them or not. So the easiest way to calculate a determinant is to choose a column or a row and expand in cofactors. And over here I have a very nice column because it has 2 zeros in it. So the cofactors that multiply these zeros disappear. And the determinant then is going to be, it's going to go plus, minus, plus, minus, plus. So the determinant of JB is equal to positive 1 times the determinant of this part over here. So that's going to be this times this, which is I left something off here. What is that? A sine? Okay. So it's going to be sine theta, sine psi times a negative sine phi. So it's going to be a negative sine squared phi. It's going to be this times this minus this times this. So minus, and that's going to be a sine theta cosine squared psi. But we have our old friend here, sine squared plus cosine squared equals 1. So this result is going to be negative sine of theta. Okay, and if we do the same thing over here, except now I'm going to choose this column because it's convenient as zeros and ones. And it's going to be plus minus plus, so it's going to be 1 times this minus this times this. And it's actually going to be the same thing. The determinant of Js is also equal to negative sine theta. Now, actually, I didn't need to calculate that determinant independently. If I know the determinant of Jb, I automatically know the determinant of Js and vice versa. And the reason for that is because I know how the angular velocities are related to each other. If omega s is equal to r times omega b, and if I make a simple substitution, if I say omega s is equal to r times omega b, but I know that omega s is Js times phi dot. Here I'm suppressing the dependence on phi. It still depends on phi, I'm just not writing it to save a little bit of writing. And over here, I know that this one is equal to Jb times phi dot. Okay. So